A second mathematical structure that will be of interest to us is a vector space. So this is going to be a collection of mathematical objects, which we're going to call vectors. Okay? That are endowed, again, with two operations. But here we have to be very careful. Okay? We're going to associate our vector space with a field. All right, we're again going to have these two operations. Addition and scalar multiplication. Under which it is closed. All right? So once again, that means that addition and scalar multiplication cannot be used to exit the vector field. Okay? We're going to be using this notation for our vectors. All right, this is called a ket. And it's a convenient notation to use, even though we don't use it in the linear algebra class. All right? So if V is in my vector space, and U is also in my vector space, and C and D are in my field, then U plus V is in my vector space, and CB is in my vector space. All right? That's the statement of closure. I can add any two elements of my vector space together, and I'll get another element of my vector space. I can multiply any element of my vector space by a scalar, and I'll get another element of my vector space. All right? Now, this addition operation is also associative and commutative. There's also an additive identity, which some authors use the ket notation for. I've never been comfortable with that. Sometimes there are other things that aren't the additive identity that I want to use that symbol for. So I'm just going to say 0. Okay? There's an additive identity 0 in my vector space that has the standard properties of an additive identity. If I add the additive identity to any vector in my space, I just get the same vector. It doesn't do anything. Addition of the additive identity leaves every element invariant. It doesn't change. We also have an additive inverse. Such that V plus its additive inverse is equal to the additive identity. All right? All right. Now, I already said that this was a commutative operation. Okay? Let's look at the scalar multiplication operation. These properties are a little bit more subtle because they relate the vector field, or sorry, they relate the vector space to the field. Okay? So, let's see how this would work. The scalar multiplication operation is associative. What does that mean? Well, if I start off with vector v, I can multiply it by the scalar d. Because the vector space is closed under scalar multiplication, this will give me another vector in my vector space. Now I can take this new vector in my vector space and multiply it by the scalar c, and I'll get another vector in my vector space. Saying that this operation is associative means that this is the same as that. Now, I mean, this looks sort of obvious on its surface, but if we think about it, these operations are both scalar multiplication. So I did scalar multiplication twice. Here, this multiplication operation took place in the field. This is a product between two elements of the field. Because the field is closed under multiplication, c times d is another element of the field. And now, I do scalar multiplication with a new element of the field on V, and I get the same thing. All right? We have something similar with the distributive property. I could say that. All right? So here I add the vectors together in the vector space, and then I do a scalar multiplication on that sum. On the right-hand side, I do the scalar multiplications first, and then I add in the vector space. Okay. We, of course, also have and this is kind of interesting because this addition operation is taking place in the field. I get a new number in the field, and then I do scalar multiplication. This addition operation is taking place in the vector space. All right, you see all the difference there? Okay? At any rate, they're all standard properties, but sometimes it's worthwhile to think carefully about where the operations are taking place. All right? At any rate, that is what a vector space is. It's a collection of objects closed under addition and scalar multiplication. One big difference between a vector space and a field is that vector spaces do not have a standard multiplication operation. I do have an addition operation. Given any vectors in the vector space, I can form their sum, and that gives me another vector in the vector space. But there's no way to multiply the two vectors together. Okay? It's not defined. There isn't a multiplication operation. Vector spaces do not require that. I have addition and I have scalar multiplication. Okay? And so that defines a vector space.